thank you very much for this opportunity to speak. In spite of being one of organizers, it's not very traditional to speak for organizers, but other people, other organizers kindly propose me to speak as well. And I'm sorry that I'm speaking not with my own voice. It's a little bit because of my bronchitis. Sorry. And also, I want to say just a very short explanation why I choose this subject, because as I told yesterday, unfortunately, I was not very close, neither mathematically nor personally, to Anatoly Moiseyevich Vershik, though I always admired his ideas, his papers, which I've used, 2 or 3 papers I've used very heavily, and his position in different aspects of mathematical and social life. And I discussed some things which are not far from interest of Anatoly Moiseyevich Vershik, and one of these subjects is a story of N-valued groups, and it is one of my subjects in this talk. But a main hero of my talks are so my plan, if I succeed, I never succeed to have a proper time, but if I succeed, I will discuss motivations and main actors of my talk. Then I will try to explain how to go from non-abelian similar to Abel statement to what we call non-abelian Abel theorem, to multiplication kernels. And oh, I'm sorry, I forgot to say that my talk is very, very heavily based on ideas of Maxim, which he shared with different people and with me during the last 14 years. We started these discussions in 2011, I think. And I was very grateful to my co-authors, Veselov, Anton Melit, Duka van Straten, Ilya Gaiur, very, very recently, but very nicely entered in this discussion, and Viktor Buchstaber, who inspired me to connect what we did with Ilya and Duka with N-valued groups. So then I will explain briefly what I understand under Bessel and N-Bessel function and their kernels, and what is beyond of this, and then how it relates to Buchstaber-Rees and valued group description. Then I will briefly explain the relation between so-called Buchstaber and Kontsevich polynomials, which was the original stupid question. As usual, I always have very stupid questions. I look at 2 polynomials, and then I will show you. So what the objects I want to discuss. The first object, it's recently very popular multiplication kernel story. Recently, it means after publication of paper of Maxim and Shurikadesky in 2021. But the story of multiplication kernels goes back to 19th century. You will see this, and I will give you a timeline of it. And multiplication kernel, it's something which is very, very intimately related to so-called quantum differential operator of projective space of dimension n-1 in sense of Dubrovin and Sasha Giventhal. And this is what I called N-Bessel equation in my talk, or more precisely, it's not Bessel, it's N-Klosterman equation, as people of number theory use this in their terminology. So Buchstaber polynomial also in the title of my talk. And this is a very simple and very nice polynomial. What I want to draw your attention, I want to draw your attention that this is a symmetric polynomial in 3 variables with three parameters. And symmetricity I just stressed by using elementary symmetric expressions for sigma 1, it's sum of x, y, z, sigma 3 product, and sigma 2 pairwise products. And also these parameters a1, a3, a2. And the form of this polynomial gives you idea that there is some quadratic trinome for which this polynomial is a kind of discriminant. So it's a discriminant type polynomial. What we call generalized Kontsevich polynomials, I think that the name generalized because we also consider 3 parameters. It was in our discussions with Vasily, Anton, and even Maxim, or in some stage discussed it. So this also a polynomial of discriminant type. So this is clearly written the discriminant of the quadratic polynomial in variable t. Coefficients of these polynomials are symmetric functions in x, y, z, sigma 1, sigma 2, sigma 3, and also depending on 3 parameters a, b, c, which is the reason why it is called generalized. In fact, Maxim, when he introduced this polynomial, he used a special value of this a, b, c, and you will see that it is not a big generalization. It is just the difference is how you write a cubic polynomial in Legendre form or in general form. Well, now just origins of what I will try to tell you. The first is a famous Clausen duplication formula for hypergeometric functions. It's a square of Gaussian hypergeometry with special values of parameters a, b, and c. And this square equals to hypergeometry of type 3-2 with parameters which explicitly related to initial a, b parameters of this. This formula was obtained by Clausen in, you see, in 1828, and he published it in Krell under the title which is written here. It was the title of his paper. And it was very, very useful in many problems. Duplication formula. Recently, interest to this type formulas was motivated by Duke van Straten and Vadim Zudilin and Almquist in their paper about so-called Calabi-Yau differential operators, where when they heavily used this formula and some analogs of it for. And it is interesting that what I want to tell you today, it is a kind of this formula, but for the generation of hypergeometry, so it's so-called confluent hypergeometry of type 0, 1. So if we take this degeneration, in the point nx over 2 and ny over 2, the product of these two functions can be expressed in the function in some kind. It is a kind of average meaning theorem for in spherical functions. So this very nice formula was discovered Schläfli. Of course, he didn't speak about spherical functions. He just wrote it explicitly in terms of degenerate hypergeometry. But you will see that this is a kind of a theorem of average for this degeneration, or in more formal mathematical language, you can say that this product formula is a structure of homogeneous commutative coalgebra of ON invariant functions on symmetric space Rn. And well, it is a very
this is 0f(n) Bessel functions.
Yes, yes, of course. And I will show you this formula in a different way just here. So this is the same formula. Okay. And this formula more known for people in special functions and in complex analysis. It is so-called Sonine Gegenbauer formula. And this formula relates product of two Bessel functions in points x, y through integral of Bessel functions in the point z with some measure z dz and kernel, which is algebraic and beautiful. This is a quartic formula, and this is a quartic polynomial, which I will show many interesting avatars of this polynomial. Well, this is a classical story of 19th century as well. And finally, timeline is finished with so-called appearance of Kontsevich polynomials in the same form of multiplication product of two eigenfunctions for this differential equation, which is so-called D2 in some slang differential equation with the function, cubic function f. In fact, it is a kind of Hoyne differential operator, and eigenproblem for this operator gives you functions phi sub lambda, phi in x and y, and then you can integrate this with the kernel square root of this Kontsevich polynomial. This is not generalized; it is natural Kontsevich polynomial. Well, so this is origins and motivations of my talk. And why Maxim was interested in this, of course, he can explain it better than me, but I will briefly say that he introduced this polynomial in very, very useful and important paper in 2007 about non-commutative, about motifs in non-zero characteristics. And he wanted to compute number of Hecke operators for local system over sphere minus 4 points over finite field f sub p, and the formula for Hecke eigenvectors for product of Hecke eigenfunctions gives you this Hecke operators in matrix form in his paper. And he conjectured that number of these Hecke operators very, very explicitly related to number of solutions of some polynomial equation over f sub p. And this polynomial equation includes this polynomial p. Natural question, what's happened if you replace f sub p by other field, for example, for complex numbers c. It was solved by Kazhdan and Ettinghoff with Frenkel in their approach to so-called analytic geometric Lagrange. They used idea of Maxim with this polynomial, with the same polynomial, and wrote very, very similar formula in some space. Details I will not explain you because this
formula was already in my paper, but they completely forgot. They rediscovered it.
So, sorry?
No, it's different. I have formulas in my paper for local fields as well, and then it was completely forgotten. They just rediscovered.
They rediscovered it.
Rediscovered and so
I suppose that it was your talk.
No. I told him. I already talked to you 12 years before. You completely forgot. I talked to Dima and yeah.
Well, you told it about this polynomial to so many people, and everybody forgot about it.
Yes.
Okay. Anyway, I'm sorry. I was wrong historically, but miraculously, polynomials are exactly the same. This is my hero generalized Kontsevich polynomial. So what I repeat again, the stupid question which I asked myself, and it was a trigger. I look at Kontsevich polynomial and said, I saw something very similar. Very similar by property, different visibly. And then I remember that many years ago, in 1990, I read a paper of Buchstaber about polynomials which govern formal group law for elliptic formal groups. And this polynomial, Buchstaber polynomial, which defined this law, had similar property like Maxim's polynomial, but it looked very different. And then at some point we understood, I made many stupid computations and understood that it is just a Möbius transformation one to another. That's the main result.
Just another coordinate, yeah?
Yes. We can stop here because it was the main result. But in the way, I will show you something beautiful, which was much more interesting than the just direct relation between Kontsevich and Buchstaber polynomials. So first, I will remind you that the group law in different variations, a relation between multiplication theorems and addition theorems, it is a classical story, and it is just an advertisement of this logarithm, additivity and multiplicativity, or trigonometric theorems, or the most interesting, of course, it's the first non-trivial relation. It is so-called Landin transform, which was used by Euler when he tried to find the length of Lemniscate arc. This is a really elliptic function addition law. Well, this is also a kind of advertisement. Everybody knows how geometrically you can interpret addition on the elliptic curve in Weierstrass with this differential omega, and then this law can be rewritten instead of geometrically, can be written in form of differential equations. So we can consider a line bundle with connection, and for this differential equation has exponential solution of this integral, and exponential property gives you a link between products of sections and addition of integrals with this differential by modulo of lattice, of course. And this theorem was in the same year. You see, it is interesting. 1828. I will show you one, if I have time, anecdote about this year. In this year, Bessel wrote a letter to Gauss, and it was a letter, kind of letter against Abel. He wrote that Abel published something which Gauss should publish but didn't do, and this young guy, it was a kind of very negative letter of Bessel about Abel publication. So it was the same year. So what Abel published? He published the following result. If we have, instead of elliptic curve, hyperelliptic curve, and this rational differential omega, then taking a number of points x1, xn, and integrals, sum of integrals of this rational differential, we can find reduction of a number of point and express this sum in sum of integrals for p point, where p is many times less than n. Adding some good function, holomorphic or maybe logarithmic, but anyway, we can reduce the number of integration passes. This what Abelian-Abel theorem. If we go to
is P the same as genus or not?
Yeah. Yes. It's possible. Yes. And this theorem admit multiplicative interpretation, which is important for me, because now instead of a line bundle, I can consider vector bundle, and instead of vector bundle, in the vector bundles, I can use the most general differential equation, and then a product of sections I can express in integral with the kernel kxy, and the product of my sections in the point P. So it's just the same theorem written in also Abelian-Abel theorem, but written in multiplicative way. Of course, it can be interpreted like some kind of delta kernel, which you will see in elementary example immediately. So, non-Abelian version of Abel theorem, as I told you, it's you replace Abelian line bundle by vector bundles, and you can consider multiplication formula for equation with differential operator L, and lambda here plays also a role so-called accessory parameter. The local monodromy of this equation doesn't depend on lambda, which implies that my future kernel also independent on lambda. So I want to study the formula product of two solutions with some kernel k, which is independent on lambda, and solution I will search in the form of series on this generating function with coefficients which are polynomials in lambda, and degree of these polynomials Maxim and Sasha proposed in the following very beautiful form, which I had a long discussion with Odesky, and I called it theorem, and Odesky said, no, it is just a lemma. So, but lemma is quite beautiful. Let's consider these coefficients in generating functions such that the index of polynomial has its degree. So it's constant, degree 1, and etc. Then the product of P sub I, P sub j, it's a kind of associativity constant Cijk in this series. And if we have this generating function and want to write the multiplication formula for them in x and y, then the kernel admit the beautiful expression with this constant Cijk. And of course, this formula immediately gives you idea how to generalize it for polynomials of any number of variables. So instead of binary operation, we can write a formula which a kind of reduction of G plus 1 to G products, like it was in Abel theorem. Such formulas are very important. I just say that I had a long discussion with Tom Kurnwinder, one of the most important persons in special function of our days. And he said that if we take any system of orthogonal polynomials with some measure mu, then canonical problem, there are 3 canonical problems. I will not enlist all of them. But the first Tom said that the first problem in orthogonal polynomial series always was this formula, which I called multiplication, and they called product formula. So product of 2 polynomials in x and y, you should find the kernel for this measure with z under integral. And of course, the kernel, it is the product of these polynomials. It is very explicit in this case. It is not a big secret that people knew many such product formulas and many such formulas. What is interesting, and that if you have kernel non-negative, that it is a kind of aspect of so-called hypergroup theories associated with orthogonal polynomials. And this is not far from two-valued groups, which I will discuss later. But it is a different and very interesting, huge subject, which I have no time to discuss. A main example which I want to show you is so-called Gegenbauer polynomials. It is the same Gegenbauer, but not the same product formula. Sorry. If we have such differential equation, what's happened? If we have such differential equation and solutions g0 sub n, which depends on cosine 2 times theta, this equation in this form can be written in product formula. Solution of this equation gives you the kernel of algebraic type also. And it is interesting, cubic polynomial under the square root. X, y, z, it's a cosine to theta, etc. So zero locus of this cubic, it is so-called nodal or conic Cayley cubic. And this cubic relates to very famous Mordell cubic after some changing of variables. And this law appeared in Buchstaber polynomial form and in the formal group which governs the case theory formal group law. I will probably say a few words later about it. But the link between Gegenbauer polynomials and this locus, it is just observation. We don't know if it is very deep observation, but...
But there's also Markov cubic, yeah, which is...
Sorry?
There's also Markov cubic, which looks...
Oh, yes. Of course, it comes from... absolutely. Now, I want to my favorite part of this talk. It's Bessel and beyond. So I want to discuss another product formula. I will start with a reminder, a Bessel operator. The simplest Bessel operator, it's just x dx, and I want to use this Euler operator for eigenvalue problem for derivation d over dx. So you have exponential, nobody forget it, and anecdotes about it. And multiplication for exponential gives you addition formula here, and representation in the kernel formula with the delta kernel taken in the point x plus y minus z. Or alternatively, you can write, it is the same, you can write it in Cauchy form, or you integrate over z, over circle, which is with a radius equal to x plus y. And it gives you possibility to write the kernel for Bessel 1, which I denote K1, in this rational form. Okay. Two Bessel, it's you take Euler operator, and you write this as a, like I told you, quantum P1 Dubrovin Giventhaler differential operator, this one. A solution of this operator can be written explicitly. I use this normalization because it's much simpler than usual Bessel, zero Bessel. It is modified Bessel in the point 2 square root of lambda x. Then the series, you avoid the coefficient 4, you avoid -1, etc. And it is not simply avoiding this. If you take Sonine Gegenbauer formula, instead of quartic, you see conic. You see conic, very nice, and you don't have z dz. Okay, go further. Take any n. So we have really Pn-1 quantum differential operator, and we have solution, analytic. I don't see that, of course, you know very well that Bessel equation has two solutions. I'm interested in analytic solutions in zero. There is also a solution in infinity, which has a Stokes data, which in some sense interesting to discuss maybe later. For the reasons of n group values. But I will also interested in analytic solutions, so I will consider only such nice series. Instead of n, 2, I will have n, any n, and taking accessory parameter equal to 1, I have the product formula in binomial series form, and then, of course, I can rewrite it in the form of, in Cauchy residual form, and thinking about x, y, z like projective homogeneous coordinates goes to affine part, I will write it as integral of hn, which is simply binomial series in two variables y and x. Okay, so the property of this kernel, using Maxim and Schorik formula, it is a very nice series. And using this, we proved with Ilya and Duka that considering such hypersurface in torus of dimension n-1, this torus has a period given by Poincare residue formula, and this period function, it is exactly our kernel if we write it in coordinates x over z, y over z. So this is one of our results. Of course, we have much more results about the relation with some motivic interpretation of this N-Bessel kernel, but it is very far from subject of my talk. Instead,
here genus of spectral curve is not one. Spectral curve has not genus here.
No. No.
What?
What do you mean spectral?
No, because our story with kernels, it was some spectral curve in a plane moving, yeah. And is it, yeah, because in general it has some genus and that, like g plus 1 function from like g function, but here from 2 to 1. So
yes, this is just simplest one. Yeah.
Genus 1, yeah.
This is genus 1, but we have multivariable as well. I say that it is very far from. Okay. No, we have all this. We have. If you look the paper with Duka, you will see many interesting multiplication formulas for this. Now I want to go to a singularity theory. It means that I want to see the singularity loci of these D modules for my kernel. So for n equal 2, you remember I have this Bessel conic. I called it Bessel conic. But in future, you will see that it is always coincide with so-called Buchstaber polynomial with parameters 0, 0, 0. Geometrically, in P2, the zero locus defined this triangle with a conic which touched the XYZ axis, x equal to 0, y equal to 0, z equal to 0 in the midpoints. And if you go to so-called Kummer, if you go to so-called Kummer lift, it means that instead of XYZ, you go again back to quartic. Then this quartic factorizes in Heron formula type and equals to 16 squares of area of this triangle. So this is not occasional result. And if you take any n, then these singularities of my kernels, they have a form triangle XYZ times irreducible part, and this irreducible part given by this symmetric polynomials, which has n-1, n-2 over 2 double points, and it has inflection points touched and intersect coordinate triangle always in the midpoints intersect only. And factorizes after Kummer lift, if you replace XYZ by nth degree of it, as a product of linear combinations of U, V, and W, and coefficients of these combinations are square root of unity degree 1. Moreover, we can prove the following theorem. This polynomial also has a discriminant form. And this discriminant form is a discriminant in variable t of polynomial in t degree 2 times n minus 2, written in this combination, linear combination x, y, z with coefficients of t to n minus 1 and etc. So, and it is a reducible part. And it should be to have the full discriminant, you should multiply it x, y, z in degree n minus 2. Now, I will quickly remind what is the Buchstaber-Rees and valued groups. First, I start with two-valued group. If you don't know what it is, it's very, very simple thing. It's a set with a low binary law, any set X, and it's a map of Cartesian product of this set to symmetric square of X with some unit element E and the inverse element X minus 1. And the axioms of this group are the following. The main axiom is associativity. And this associativity, it means that there is for any 3 elements of X, you have coincidence of 4 element sets. So it is left-hand side and right-hand side. It's elements in with 4 sets, and these elements coincide. I will show you an example what I have in mind. The strong unity associativity means that if you take this composition with E, left and right, it gives you diagonal XX element in symmetric square. And existence of inverse, it means that if you take X times X minus 1 and X minus 1 times X, these two sets always contain the natural element. These two axioms, especially the last one, it is a main difference in definition with usual, which differs two-valued groups from usual groups. Otherwise, I can say that it was studied by Alexander Barvinek later when Buchstaber published his paper about N-valued group. Barvinek proved that, for example, some beautiful results for N groups which don't coincide with similar results for groups. For example, famous Lagrange theorem doesn't work for n-valued group. Oops. Example, and it is important example for me. Let's consider C, and we consider second order automorphism, which is just multiplication by square root of 1. So we have quotient C over Z2, and multiplication law, which I defined by this expression. So we have in symmetric square, we have this two elements, square root of x plus square root of y in square, and the difference in square. The unity, it is 0, and the inverse of z, it's itself z. So if you look at this, you see that these expressions, they are roots of polynomial f x y z, z square minus 2x plus y times z, x minus 1 y square, and it is written as a discriminant of the following expression. So you can verify that two-valued multiplication defining by these two roots of this polynomial equation, you can check immediately. All axioms, here I check it. It is a very nice exercise. And also I want to show very nice simple exercise that this polynomial, it is a splitted polynomial. It means that if we take discriminant of this polynomial in Z, this polynomial represents like a product of f of x, f of y, where f, it is just linear. And it is a degeneration of property of future Buchstaber-Kontsevich family of polynomials. And another interesting, I can't omit it instead of lack of time, that this polynomial is nothing but so-called Kalin function. Kalin, it's a beautiful story. It's a Swedish physicist, very famous in early 60s. He was the author of idea of CERN. He was a creator of CERN, Kalin. And also he was very famous teacher. He wrote a handbook about elementary particle physics, and especially about some computations of amplitude computations. And in this book, he introduced so-called Kalin function. This Kalin function lambda, it is in fact this function which is a Buchstaber polynomial with parameter 0 or Bessel conic singular polynomial. So if we go to again to geometry, we have that this Kalin function is relates to Heron formula. But Kalin also discovered that in kinematic of these scattering particles and in computation of Feynman integrals, in the simplest one-loop case, Kalin function. These Kalin functions can appear in the form of minor of Kelly-Menger determinant. I omit this one row and column, but this is exactly Kelly-Menger determinant for n equal to 2. And this Kalin function expressed in terms of square of mass and square of difference for momentum. So z, it's a square of difference of momentum, and x and y, square of mass of scattering particles. And it means that we have a relation that a vanishing locus of Bessel, it is simplest Landau singularity, and the equation is the simplest Landau variety. And also it shows that all other interesting relations with Feynman integrals also takes place. How much time? Huh? No more time. Okay, I told you just one thing I want to tell you. Then if you take, instead of two valued groups, we consider n-valued groups. So this is interpretation, which everybody understands how this law works for usual elliptic curve. And this is a model Markov Gegenbauer law, which I mentioned for Gegenbauer polynomials. And then if you take n-valued groups, then this example of n-valued groups gives you a discriminant description, and the theorem that N-Bessel product formula gives you Buchstaber-Rees n-valued group laws. And these Buchstaber-Rees, they are always factorizes, like I told you, after this Kummer lift. Fortunately, I told you the main result. What's the relation between two beautiful families of polynomials? This relation is that they are transformed one to another by Möbius transformation. And all description will appear in the paper which we put in archive maybe next week. Thank you.
Any good questions?
Do you have any relations to caustics and to
yes, it's all this loci. They are loci from Arnold type.
And can
yes,
you classify?
it's lambda. It's discriminant singularities. You see. Yes, it should be also explored how this.
More questions? Let's thank Volodya again.
Sorry.